Okay, so we're going to wrap up the chi-square goodness of fit test when the expected frequencies are known. So essentially what we did was we calculated the expected frequencies by multiplying the proportion within the United States against the sample size. We then did the difference between the observed and the expected frequencies. So, this column minus this column, that gave us this value. We then squared that value, and then we divided that value by the expected frequency. And the last thing we need to do to calculate our chi-square then is to simply add up these values. So my apologies once again. So if we do this, 7 plus 6 is 13, 14, 21, 26. Carry the 2, and 8 is 10, and 5 is 15, 19. We're going to carry the 1, 9, and 2 is 11, 13, 14. So what this is telling us is that our obtained chi-square is chi-squared obtained is equal to 14.96. So we can compare that with our critical value. We can see pretty clearly that 14.96 is going to exceed our value of 9.488. So we're going to make the decision to reject the null. And so as in all of our other cases, we're going to need to type in a sentence. And so we're going to conclude that the distribution of different types of pets among TU, U students does not match the distribution of pets. Let's say different types of pets, different types of pets in the U.S. population. And then we're going to say reject the null. And let's see if we can do this. Change that to a symbol. Okay, and oops, sorry. And we will try and select that. Okay, never mind. So I'm just going to write it out, but you would most likely, so chi-square, and then we're going to put it on 4 degrees of freedom is equal to 14, goodness gracious, 14.9. Jeez. And then, sorry, P less than 0.05. Okay, there we go. Space. We'll try that again. P is less than. Oh, I see. That's not the less than sign. Huh. Where is my less than sign? All right, we're just going to. Oh, wait, nope. We're just going to do it this way. We're going to just say less than 0.05 so we don't waste time. Okay. All right. So that's basically the chi-square goodness of fit test when the expected frequencies are known. Okay, now the next thing that we need to do is learn how to calculate the chi-square goodness of fit test when the expected frequencies are not known. So in this example, we're interested in knowing whether the number of students who register for intra-psych courses differs by the time of day. So we look at enrollments in intra-psych courses at 5 times a day on Tuesdays and Thursdays, and we obtain the numbers in the table below. So notice here that we do not have a directional test, right? But directional and non-directional is less important for chi-square. But we just want to know, okay, do the numbers of students that are represented in this table here differ from what we would expect at each of the times a day? Now, because we don't have a specific set of values, what we need to do is we need to determine an expected frequency. So generally speaking, when we're doing this, we will make the assumption that the expected frequency for enrollments in each of the times a day would be equal. And that's really how we do that. Okay, but the first thing we need to do, of course, is specify our hypotheses once again. And we're going to say that, so our H sub 0 is going to be that the number of students enrolled in classes does not differ based on time of day. And then we can select this whole thing here, and we're going to copy that. And our H sub 1 then is going to be, sorry, okay. All right, sorry, I decided to stop that so you didn't have to see me fighting with my computer. So we're going to just, oops. And yet, once again, you'll see me fighting with my computer. And that is also not what I wanted to do. There we go. So we're going to say it does differ by time of day. Okay. Whew. All right, so our hypotheses are specified. And then what we need to do is, again, look for our critical values. So again, the degrees of freedom are going to be k minus 1. So k is the number of groups. We've got 1, 2, 3, 4, 5 groups. So we've got 5 minus 1 again, which is 4. So our chi-square critical value is once again going to be 9.488. Okay, so in this case, it's much simpler. In order for us to determine the expected frequencies, because we don't know them, we're simply going to assume that there are going to be equal numbers of students in each of the different time points. So all we do is we take n, okay, and so f sub e is going to be equal to k. It's going to be actually n, and we're going to divide that by k. So that's going to be 173 divided by 5, and that's going to give us a value of 34 0.6, and we're going to count that as the expected frequency for all 5 class times. Okay, so essentially what we're saying is that if our null hypothesis is true, then there should be equal numbers of students enrolled in each one of these classrooms, and that these numbers do not significantly different from what we would expect. And then we just basically do it the same way. So we're now going to, we're using the same formula, we're going to do our observed minus our expected frequency. So 25 minus 34.6 is going to be negative 9.6. 40 minus 34.6 is 5.4. 45 minus 34.6 is 10.4. 35 minus 34.6 is 0.4. And then finally 28 minus 34.6 is minus 6.6. And again, to make sure, oh, well, never mind, we would add this up, right? So this we should know is correct, right? 6 and 6 is 12, 18, 24, 30. 3 and 4 is 7, 11, 15, 19. What did I do here? Hold on. 6 times 5 is 30. 3 and 4 is 7, 11, 15, 19. 23. I carry the 2, and 3 is 5, and 3 is 8, and 3 is 11, and 3 is 14. So that gives us 173. So verifying that we did the math right. Okay, so now in order to do the next step, we need to take the square of the difference between the observed and the expected frequencies. So negative 9.6 squared is going to be 92.16. 5.4 squared is 29.16. 10.4 squared is 108.16. 0.4 squared is 0.16, 0.16, and negative 6.6 squared is going to be 43.66. Okay, and then last step again is we want to now divide this squared difference between the observed and the expected frequencies by the expected frequency, in which case this is actually 34.96. So we're going to do 92.16 divided by 34.16, right? And then we're going to do 29.16 divided by 0.6. Right, and then we'll do 108.16 divided by 34.6, and so on and so forth. All right, and so that's going to give us values of 2.66, 0.84, 3.13, 0.005, and 1.26. So if we're going to add this all up, I haven't aligned this very well, but the correct answer here would be 7.895, or if you wanted to round to 20, it would be 7.90. So we have our critical value here of 9.488. We have our obtained value here of 7.9. So it's pretty clear that we are not going to reject the null hypothesis in this case. And so to make this as simple as possible, we're just going to copy that, and we're going to report our results. And we're going to say does not differ depending on the time based on the time of day, except the null, comma, and again we're going to have chi-square on, and this is 4 degrees of freedom once again, is equal to 7.90, comma, p, and once again, I don't know where my less than is on my tablet keyboard, so we're just going to do this.